Hi, welcome back to the course on mechanics. This is still Ken and we're on lesson 8 of the course on momentum, impulse, and collisions. And this will be our goals for this lesson. First, we're going to learn the meaning of the momentum of particle and how an impulse causes it to change. And we're going to learn how to use the conservation of momentum. And lastly, we're going to learn how to solve problems involving collisions. We begin with our study on momentum and impulse. For a short introduction about the topic, in many situations, such as what we have here, you have a bullet hitting a carrot, we cannot use Newton's second law to solve problems because we know very little about complicated forces involved. If you're going to analyze the problem here of how the carrot explodes once the bullet hits it, you cannot completely understand the phenomenon just by using your Newton's second law. So in this lesson, we shall introduce momentum and impulse and then the conservation of momentum to solve problems such as this one. Momentum is a word that we hear used colloquially in everyday life. Like say for example, you say that I'm in the momentum to do something. So when you're talking about that one, meaning you are at the point wherein nobody can stop you from doing that thing. We are often told that sports teams and political candidates had a lot of momentum, and you will usually hear this one when you're watching sports games. But in this context, when we say that the sports team, has a lot of momentum, the speaker usually means to imply that the team or candidate has a lot of recent successes, and that it would be difficult for an opponent to change their trajectory. But what is really momentum, and is momentum defined differently in physics? Well, we can safely say that this is the same essence of the meaning of momentum in physics, though in physics we need to be more precise. Momentum is a measurement of mass in motion. It means how much mass is in how much motion. It is usually given by the symbol P. If you can see on the images, we have your Newton's cradle, and you even have two cherries colliding each other. What we have here are actually objects transferring their momentum to the nearby object. And these are things, or these are masses which are in motion. And we're actually studying here how much mass is in how much motion. So we're actually taking here two special quantities. You have your mass and then your velocity. The momentum of a particle is the product of its mass and its velocity. As I've said in the previous slide, we're taking here your two quantities. You have your mass and then your velocity. And if you can remember your Newton's second law, which is your force is equal to mass times your acceleration, your Newton's second law can be written in terms of the momentum. So let's do it. Let's do the calculation. So again, your second law is you have the sum of all your F is equal to your mass times your acceleration. But if you can remember, your acceleration is just the time derivative of your velocity, dv over dt. And substituting this one to the Newton's second law equation, you have the sum of all your F is equal to your mass times your dv over dt. But we can take your mass into the time derivative so that we have your d mv over dt. Now your mass times your velocity is just your momentum v. So your mass times your velocity vector is again just your momentum. So thus we can write your Newton's second law as the change in the time derivative change of your momentum gp over dt. Now this is a different form with your mass times your acceleration formula, and this form your summation of all your F is equal to your dp over dt is actually the original statement of Newton's second law. So this is the original one. So it was not really actually your mass times your acceleration that Newton usually expressed your second law, but it was in terms of your momentum. That's why in higher classical mechanics classes, you would usually define your Newton's second law as the time derivative, the time rate of change of your momentum. So a rapid change in momentum requires a large net force, uh, as you can see in this equation. So again, a rapid change in momentum requires a large net force, while a gradual change in momentum requires less net force. So of course, when you have a greater change of your dp, you would require a greater F. But if this change of your momentum is is gradual, I mean earlier when you have a rapid change of your momentum, this one here, meaning you have, let's say, some big change in your momentum, then you would require some great net force for this change in your momentum. But if the change in your momentum is gradual, meaning slowly, it would only require you a little F. And this is actually the physics behind your airbags, which are used in your cars. So in fast moving automobile, or if a fast moving automobile stops suddenly in a collision, like say for example you hit a wall or you hit another car, the driver's momentum, that is the mass times velocity, changes from a large value to zero in a short time. So here, your dp over dt changes rapidly. So again, the driver's momentum changes from a large value to zero in a short time. If you are traveling more faster than your current speed and you need to stop to zero, then that would mean a greater change in your momentum. So that is the purpose of your airbag. An airbag causes the driver to lose momentum more gradually than would an abrupt collision with the steering wheel. It reducing the force exerted on the driver as well as the possibility of injury. So if you're going to compare this one here in this image here, if you're going to look at, if there was no airbag on the steering wheel, then the head of the driver would collide more faster to the steering wheel as compared to when there is an airbag. So the airbag is saving you because of this gradual change in the momentum. So your airbag helps by giving your change in momentum to be a little bit more gradual. Okay, so that's why when you're going to buy your car or when you are going to ride your car, it's very important that you check your airbags just to just for precautionary measures. So now let's talk about your impulse and your momentum. What is impulse? Impulse is a term that quantifies the overall effect of a force acting over your time. So here, your impulse of the net force, denoted by J, is defined to be your vector J is equal to the sum of all your F times your change in your time. You have T2 minus T1. So again, it's a term that quantifies the overall effect of a force acting over time. The SI unit of your impulse is in Newton times second. If the net force is constant, then dp over dt is also constant, and you can play with your equation. Okay, so this is again your Newton's second law here. So you have here your Newton's second law, and Again, if the net force here is constant, then your dp over dt is also constant. So you can change it so that you have your p2 minus your p1, your final momentum minus your initial momentum over your t2 minus t1. And if you multiply both sides by your t2 minus t1, so what we have here is this equation here. So the sum of all your f is equal to your t2 minus the sum of all your f times t2 minus t1 is equal to the change in your momentum. Or here, since this is just your impulse is equal to the change in your momentum. And thus we have here your impulse momentum theorem. So the impulse momentum theorem says that the change in momentum of a particle during a time interval is equal to the impulse of the net force acting on the particle during that time interval. Or in mathematical terms, you have your impulse J is equal to your P2 minus P1, which is just the change in your momentum. So again, the change in momentum of particle, your P2 minus P1, during a time interval is equal to the impulse of the net force acting on the particle during that time interval. Now, here's an interesting question. Suppose you have a choice between catching a 0.50 kilogram ball moving at 4 meters per second or a 0.10 ball moving at 20 meters per second. Which will be easier to catch? So what we have here are two balls. So one is a 0.50 kilogram ball and then the other is a 0.10 kilogram ball. So the other one is 5 times heavier than the other ball. But here, your 0.50 kilogram ball has a speed of 4 meters per second. And your smaller ball, or your ball which weigh lesser, which has a mass of 0.10 kilogram, moves at a velocity of 20 meters per second. So the bigger ball moves slowly while your smaller ball moves faster. So the smaller ball moves 5 times faster than your bigger ball. And if these two balls will be thrown to you, and you have a choice between catching the 0.50 kilogram ball or the 0.10 kilogram ball, which do you think would be easier to catch? Would you rather catch the heavier one, but it moves slowly, or would you rather catch the smaller one, but the smaller one moves faster? So which do you think would you prefer? The bigger ball or the smaller ball? Now, before answering that question, let's compare first your momentum and then your kinetic energy. So changes in the momentum depend on time over which the net force acts. So again, the change in your momentum, your P2 minus your P1, depends on the time over which the net force acts. So you have your sum of your F times your delta T. This is for your momentum. But the change in kinetic energy depends on the distance over which the net force acts. That is your K2 minus your K1 is equal to your force times your displacement S. So here again, we have the change in your momentum. And then here is your change in your kinetic energy. So in here, how are we going to apply this one in order to answer the question of which ball is easier to catch? So let's apply this one to the question. So again, the question was, suppose you have a choice between catching a 0.50 kilogram ball moving at 4 meters per second or a 0.10 kilogram ball moving at 20 meters per second. Which will be easier to catch? So would you catch the 0.50 kilogram ball moving at 4 meter per second, or would you rather catch the 0.10 kilogram ball moving at 20 meters per second? Um, in some basic thought, you might think that I'd like to catch the smaller one, the 0.10 kilogram ball, because it is it weighs lesser compared to the 0.50 kilogram ball. But again, you can see here the size is not only the thing that we are going to talk about, but we are also going to consider the speed at which these balls are moving. So let's try to see which will uh, which will be easier to catch. Now let's look at the momentum of each ball. Okay, so for the bigger ball, so you have a momentum which is equal to your mass times your velocity. So you have 0.50 kilograms times 4 meters per second. So for the bigger ball, you have a momentum which is equal to 2 kilograms that meter per second. Now for the smaller ball, you have a momentum that is equal to 0.10 kilograms times 20 meters per second. The momentum here is still equal to 2 kilograms that meter per second. So talking about the momentum, it seems that the momentum of each ball is just the same. So by the momentum alone, we cannot decide whether we're going to catch the bigger ball or the smaller ball. So let's look at another part of this one. Let's look at the kinetic energy of the two balls. So again, they have the same momentum, which is equal to 2 kilogram that meter per second. How about the kinetic energy of the balls? So the bigger ball has a kinetic energy of 1/2 mv squared. So this is equal to 1/2 0.50 kilograms times 4 meters per second squared. Here, the kinetic energy of the ball is equal to 4 joules. On the other hand, the kinetic energy of the smaller ball is equal to 1/2 times 0.10 kilograms times 20 meters per second squared. Here, the kinetic energy of the smaller ball is equal to 20 joules. So as you can see here, if you are going to compare the kinetic energy of the two balls, there would be greater energy for the smaller ball than the bigger ball. So if you're going to catch the ball with a greater energy, then it would apply more force on you as compared to the bigger ball. So here, we just cannot safely say that we catch the smaller ball and we leave the bigger ball hanging. So it's not only the size that matters, but it's also about how fast these balls are moving. So it depends. Now, since the momentum is the same for both balls, both require the same impulse to be brought to rest. But stopping the 0.10 kilogram ball requires 5 times more work than the 0.50 kilogram ball because the smaller ball has more kinetic energy. Now, let's talk about your isolated system. So, just some terms, we have the internal forces. When we say internal forces, these are forces that the particles of the system exert on each other. Like say for example, in the figure, you have two astronauts. So if astronaut A will push astronaut B and astronaut B pushes astronaut A, so those forces are what you call your internal forces. So these are the forces that the astronauts exert on each other. Another term is your external forces. These are forces exerted on any part of the system by some object outside of it. Like say for example, you have something outside of this system of your astronaut and then your of your astronauts. And let's say that this one here, you apply some force to the two. So the force that this man applies to your astronauts is your external forces. So these are again forces exerted on any part of the system by some object outside of it. And when there are no external forces, we have an isolated system. So if we're going to uh, idealize a system such that we're only going to talk about the two astronauts here, then this system will be called an isolated system. So you are not looking at the effects of whatever is outside of your isolated system. The total momentum of a system of particles is the vector sum of the momenta of the individual particles. When no external forces act on an isolated system consisting of the two astronauts shown, then the total momentum of the system is conserved. This is about your uh, conservation of your momentum, which we are going to talk about in the next video.